All right, today we're going to be talking about circumference and arc length. Notice arc length is very different from arc measure. We'll get to the differences there. So the first thing you need to remember is circumference, okay? We did this in chapter 1. So find the circumference of a circle. You can either use 2 pi times the radius, or 2 times the radius is the same as the diameter. So you could use the same formula as pi times diameter. So either one of those two formulas will calculate the circumference. And that's really because all pi is pi is the ratio of the circumference of any circle divided by its diameter. That was the first discovery of pi. That's our first calculations until we found more rigorous ways to calculate it. What that means is if I take any line segment and use that as the diameter for a circle, I could lay out that length of that diameter. I'll do it maybe in a different color. I could lay that out 1, 2, 3, and some more, right? 3.14159 yada yada times the diameters. Right? I could lay that diameter out 3 and a little bit more times going around the circle. And that's true of every single circle ever. So that ratio of the circumference divided by diameter is pi. Just a little interesting fact. Okay, so the first thing we need to be able to do is find the circumference using one of these two formulas. We'll in general use 2 pi times the radius. Okay, so another important note, what I mentioned above, is arc length and arc measure are completely different things. And this is probably the most common mistake students run into. A question asks for one and they answer the other. And that leads to a lot of docked points just because you answered a question that was not being asked. So super common mistake. The main differences here are arc measure that we've done in the past is having to do with an angle. It's in degrees. You're saying out of 360 degrees total, how much do I have? Well, I have 100 degrees out of my 360. It's kind of like a percent of the circle. I have 100 degrees out of my 360. So no matter how big or small the circle is, that's the fraction or the portion of the circle I got. Out of every circle containing 360 degrees, no matter its size, as big as a pin or as big as a planet, there's 360 degrees in a circle. And I have 100 of those degrees. So I've got around a third of the circle, regardless of size. Now, arc length is very dependent on size. Arc length is a length or distance. It's saying if I were to walk around the edge of my circle from point A to point B, how far would I have walked in feet or inches or miles, right? So this is very dependent. If the circle is the size of a little eraser or something, then a fraction of that circle, you might get a measurement like, oh, the length of this arc is a few millimeters, right? Whereas if the arc is as big as, if the circle is as big as a planet, then the same 100-degree arc might now take up thousands of miles or thousands of kilometers. So even though it's still a 100-degree arc measure, because the circle is larger or smaller, the arc length is vastly different. But the big difference here is arc length is a length. It is a distance. It is in a unit of measure like feet or inches or centimeters or kilometers. Okay. So I want to be really clear about that. I'll kind of bring that up as we move along. Okay, and then finally, just remember all the stuff we did in our last unit about circles. So for example, on this first one, we know this is a central angle. And the measure of any arc is defined to be equal to the measure of its central angle. So x here would be 100 degrees. Over here, this is an inscribed angle. And we know that an inscribed angle is equal to half the measure of its intercepted arc. So this would be 40 degrees because its vertex is on the edge of the circle. And that's true over here. The really common trick is if you have a diameter cutting a circle in half, you know the measure of half of any circle. That arc is 180 degrees. And so the inscribed angle here on the other side must be a 90-degree angle because that's half of the 180. So just some common tricks to kind of remember as we move forward, because you are going to need to find the arc measure before you can find the arc length. Okay, so arc length, and I put lots of underlining here. Length, arc length. Okay, so if you already know, or you're given, or you can use some of your tricks to find the measure of an arc out of 360 degrees total, then really what you know is what fraction of the circle you have, right? So an example here is, if I have a 110 degree arc, that's 110 degrees out of 360 total, right? 360 degrees in a circle, I've got 110. So your arc is 110 out of 360. That's the fraction of the circle we have. Okay, we don't yet know the circle's radius or size, but we know we've got that fraction of the circle, that cut of the pie. Okay, that's what we're going to use to now calculate the arc length. Because if we know the total distance around the circle, and that's the circumference that we could find, right? As long as we know the radius or the diameter, we could use our formula from up here on the very top. We could say, oh yeah, just plug it in. Then the circumference is 2 pi times the radius, or pi times diameter. So if we know the circumference, and we know this fraction here, right? We know we've got an arc that's roughly a third of the whole circle, and we know how far around it is for the whole circle, then what we could do is we could just simply multiply and say, well, the arc length is simply what fraction of the circle your arc is, right? Is it a half the circle, a third? Is it a tenth of the circle? Whatever fraction of the circle you're dealing with times the total distance around the circle, right? So if you know it's, 100 feet to walk around a circle, so it's a circumference of exactly 100 feet, and you know you have a 90 degree arc, which is a quarter of the circle, well, a quarter of 100 degrees, we would know that arc length is 25 feet, because you have a quarter of a circle, and a quarter of 150 or 100 feet is 25 feet. Okay, sorry. So simplifying that a little bit, or writing it a little more mathematically, what we've got is the arc length of some arc AB is equal to the arc measure of AB over 360 degrees. So how many degrees out of the 360? That's the same as what fraction you're dealing with, right? So arc measure over 360. And then times the total circumference here, we just use the formula 2 pi r. Okay, so simplifying it a tiny bit more, this is the way we would write it. We would say the arc length of AB is the measure of AB in degrees out of 360. So again, that's just what fraction of the circle you have. Do I have half the circle, a third the circle? And then times the total circumference, 2 pi r. Okay, so that's how we're going to do it. Now, you could actually think of it instead of as what fraction of the circle am I dealing with, and then multiply that times the circumference. You could think of it as a proportion as well. That's another common way to go about solving these. So the same formula, if we just divide both sides by 2 pi r, we get this proportion here, which is saying, well, okay, so how many degrees is my arc out of the whole circle, right? Because this is the, this is my arc out of whole circle. Well, in degrees, that fraction should be the same portion, right? If I've got half of the circle's degrees, then I've got half of the circle's length, right? So over here on the right, you'd say, well, then my arc length out of the whole circle should be the same proportion. So we just say, okay, well then, the measure of my arc in degrees out of 360, whatever fraction of the circle I've got in terms of degrees, that's the same fraction I've got in terms of length, okay? So this is the exact same formula as above. The only difference is if we multiply both sides by 2 pi r, this goes over here, and we've got fraction of the circle times 2 pi r, right? Oh, it's hard to write with this, but that's the only difference. You could use it as a proportion, or just always remember what fraction of the circle I'm dealing with times the entire circumference of the circle. Okay, so that's it. I want to mention just one last little note here, something we've used a lot in trig, so I don't want this to be a sticking point. But just before we jump into problems, remember the difference between an exact answer and an approximate answer. Sometimes the book will ask for an exact answer, and sometimes they'll ask for an approximate answer. IXL, the same thing. In class on a test, you could absolutely expect me to say, leave it as an exact answer, or estimate it or approximate it to a certain decimal place. In general in math, especially as you move forward, we like We prefer exact answers. So an exact answer is using the perfect symbol pi that has an infinite number of decimal places. So a circumference would be exactly 15 pi. Now that's accurate to the trillionth decimal place. Okay, beyond anything we could actually physically create in the real world. It's more accurate than that. It's perfectly accurate. However, we could just approximate this because in the real world, right, we only need it to a certain decimal place because that's the only thing we can use to create. And so we could use 3.14 or a more accurate one or a more precise one like 3.14159 or 22 sevens. So those are just approximations. So what I could do is I could take that 15 pi and say, I'm building a shelf. It's a circular. I don't need 17 decimal places. 2 or 3 is good enough for me. So I could say 15 times 3.14. That's around 47.10. And to the nearest millimeter, that's, good enough for me. Okay. So that's an approximate answer. A giveaway is it's got a decimal in it that stops, and there were more decimals on your calculator that you ignored, right? Or just you didn't put in all the decimals of pi. Those would be the 2 hints. An exact answer giveaway would be that it still has a pi symbol in it. Okay. All right. So let's do some examples. First, just finding circumference, just practicing with that before we actually start finding arc length. So find the circumference of the first circle. So we've got the radius here. So the circumference is 2 pi r. So that is 2 times pi times 6, or 12 pi. Now I'm going to leave my answer as an exact answer. If you wanted an approximate answer, absolutely you could do that. You could just over here write 12 times pi and say, okay, there we go. Or you could have even, so I got 37.699. If I did 12 times 3.14, whoops, that was not what I wanted. Sorry, 12 times 3.14. Notice that I'm off by a little bit. I got 0.68 and it stops instead of 0.699 and the decimal going on. So you notice how already I lost some of the detail of this. So you could actually do that. You could say, you know what? Well, C is around 37.6, and then we could stop at 8 there using 3.14, depending on what decimal place they wanted you to round to. Okay. So find the circumference of the other one. Well, we got the diameter, so I'm going to choose to use the formula pi times diameter because I'm flexible. I could use either one. So I'm going to say this is pi times 17, or circumference is 17 pi. Okay, the next one says find the radius, so we're going backwards. Anytime we ask you to do something forwards in math, we also ask you to go backwards. Well, I still know I've got the formula C equals 2 pi r, and I'm choosing r because that's what it's asking for. So I'm going to plug in what I know. Well, I know 63 is equal to 2 pi r. Now, pi is just a number. So really, this is analogous. I'll do it in a different color. This is analogous to saying 63 equals 5x, right? It's just a number times x. So I'm just going to divide by that number on both sides, right? So the number we're dealing with in this problem is 2 pi. 2 pi is 2 times 3.14, around 6 something. So we're just going to divide both sides by 2 pi. It's just a number, okay? And now we get, that cancels out, and we get that the radius is 63 divided by 2 pi. And this isn't like a square root where you need to rationalize the denominator. It's totally okay to leave a pi in the denominator as long as you've simplified the fraction. And there's no pi on top. There's no 2 on top. So that's as simplified as it gets. So the radius is 63 over 2 pi, okay? Now let's actually find some arc lengths, okay? So find the length, and again, I noticed that length, not measure, of arc AB, okay? So again, I'm just going to say that the length is equal to, and I'm going to write the fraction out of 360 degrees that my arc is, and then times it by 2 pi r. Okay, that's what I'm going to do. So I just got to figure out what fraction of my circle I'm dealing with the arc AB, and then I've got to just find out what the radius is, or the diameter. I could have used that for the circumference. Okay, so the length is, I've got a 40-degree arc measure, because the central angle is 40 degrees, so I've got a 40-degree arc. So 40 degrees out of 360 degrees times, and then 2 pi, the radius is 6. So 40 over 360, if you reduce that, you end up getting 1/9. So I've got 1/9 of my circle times 12 pi. Now multiplying these together, that's just a fraction times, I'm going to put this over 1. And so fraction times fraction, that's 12 pi over 9, which I could simplify. There's a 3 in top and bottom. So that's 4 pi over 3. And that's a great exact way to leave your answer, or an approximate depending on what you would like. Up here in the question, it never specified, so I'm going to choose to leave it as an exact answer. Okay, on the next one, again, the length is equal to, and I've got to figure out how many degrees my arc is. Well, again, I've got the central angle, so that was easy. I know this is a 120 degree arc, so I've got 120 degrees out of a total of 360. Okay, that reduces to, I've got 1/3 of my circle. So I want to find what 1/3 of the total circumference is. Well, I know I'm going to use 2 pi times the radius. So I've got a radius of 14. So that's 1/3 of 28 pi. So again, putting that over 1 and multiplying, that's just 28 pi on top, 3 on bottom. And since 3 doesn't go into 28, there's nothing to simplify. So that is the length of the arc. Okay. Now, if I want to find the length of this arc in the next problem, again, this is pretty straightforward. You got the central angle. So the length is equal to, I've got 45 degrees out of a total of 360. So the fraction of the circle we're dealing with is, sorry, I've got 1/8 of the circle. Now, I'm just comfortable with these numbers. That's why it seems so quick to me. I've been doing math a lot, and I'm used to 360 degrees and the fractions of it. You can absolutely take the steps, divide it by 5 on top and bottom, divide it by 9 on top and bottom, divide it by whatever you do in steps to get there. Sorry if it seems so easy when I do it quickly. Okay. So now I want to multiply it by the total circumference. So I've got 1/8 of the circle. That's my arc AB. Now I want to see, well, it looks like, because 8 is in the center here, it looks like 8's a diameter. So I'm going to use pi times diameter here. So I'm going to get diameter of 8. So it's 8 pi. Okay, common mistake is people switching up either the radius or the diameter. But when you label 8 in the middle, that's talking about the whole segment. If you wanted a 14, notice how they put it in the middle of this, and 6 in the middle of this. Okay, so 1/8 times 8 pi, that's just pi. So the length of that is just pi, or 3.14. And in this case, the units were feet. Okay, now let's step up the difficulty just a little bit here, okay? Now, up here it says our QPR and RPS are congruent. QPR and RPS. So these two are congruent, all right? And that's all it gives us. Okay, well, I know there's a 60-degree angle. I know we're adding up two congruent angles. Let's call them x. So I know that x plus 60 in total will add up to 360 degrees in that central area. Okay, so I'm going to just use some algebra. 2x plus 60 is 360 minus 60. So we get 2x is 300 degrees left over. Dividing by two equal angles, we get that each of those angles has to be 150 degrees. So I'll just write that in really quick. So this one's 150 degrees. This one's 150. Now, of course, since those are central angles, that's the same as the arc measure, not the arc length. Okay. All right. So I found all those. So yeah, let's go down here. Oh, look, and a couple of these just do ask for arc measures. So the measure of QRS. So notice they use 3 letters. QRS starts at Q. I'll do this in my transparent. So starting at Q, going through R, and still going, whoa, that's cool. Still going through R to S. So I'm going to add up 150 plus 150, and I get that this is 300 degrees. Okay. Let's do all the measures first because we've got that already. So QR, we figured that out. That was 150. RSQ, so I'm just going to look at this. So R to S to Q, that's 150 plus 60. So that's 210. Now let's figure out the lengths they're asking for, okay? So the first length is QRS. We know from this problem right here that the measure of that arc is 300 degrees. So we're going to use that to figure out the length, okay? So length of QRS is equal to, so I've got 300 degrees out of the total 360. That's a pretty big chunk, most of the circle. And then times the total circumference here. Notice I'm given a radius of 8 feet in the original image. So this is times 2 pi 8. Okay, so dividing a 60 in this fraction, I get that this is 5/6 of the circle times 16 pi. So over 1, I get, before I multiply those, I'm just going to divide out the 2 here. So I have an 8 and a 3. The 3 isn't going to cancel with anything else on top, so that's what I'm going to be left with. I've got 40 pi over 3 as the length of that arc. Again, it didn't tell me I should approximate this, so I'm going to leave it as 40 pi over 3. You could absolutely plug in pi is 3.14, some approximation, and get that this is a little over 40. Because pi and 3 almost cancel out, you just get a little left over. Okay, so let's look at the next one. 19 is the length of QR. So QR, that's 150 degrees, because it's always referring to the minor arc. So QR being this one right here. And we already found its measure right up here in 17. So that's 150 out of 360. That's the fraction of the circle we've got. And then times, again, we've got that same, I'm already just going to use the circumference we figured out as 16 pi. So I'm just going to throw that in here. So we got times 16 pi. Okay, so I'm going to reduce just the zeros out of this. So we got 15 out of 36. I know 3 goes into both of those. So that's 5 out of 12. This one wasn't as quick for me. That's totally okay. All right, over 1. And I'm going to notice a 4 goes into both 12 and 16. So I'm going to take out a 4. This is now a 3 and a 4. So now I can multiply those fractions. 5 times 4 gives me 20 pi on top. And 3 times 1 gives me 3 on bottom. So that is the length of QR. And finally, let's do one last one, and that's the length of RSQ. So the length of RSQ, okay, so we're going to figure out what chunk of my circle I've got out of 360 degrees, and then multiply by that whole circumference, which is all the way around the circle. The length is 16 pi. So let's look up here, RSQ. Oh, we already figured that one out too. That was 18 RSQ, so that's 210 degrees. Okay, so again, this one isn't a quick fraction for me, so let's see, I'll take out the zeros, 21 out of 36, divide by 3. So the chunk I've got is I've got now 7/12 of my circle times 16 pi. Okay, I'm going to put that over 1 to multiply these fractions. And notice again, a 4 comes out. So I'm going to turn this into a 4 and this into a 3. And so now I've got, multiplying the tops, 28 pi. Multiplying the bottoms, I got 3. So the length of that arc, which was a little over half the circle, is 28 pi over 3, or around 30 or so. Okay, so I added 1 or 2 last questions here just for fun. Now this one says find the perimeter of the shaded region. So to find the perimeter of the shaded region, I'm sorry, I had to cut that. Someone knocked at my door. So to find the area of, or the perimeter of the shaded region, we do have to make an assumption here. Right? It doesn't tell us what shape this is. Now, if we don't know this is a parallelogram or a rectangle, then we can't assume this opposite side is congruent without some demarcation. And so we need to know this opposite side is congruent to know that length. We also need to know the opposite sides are congruent to know the diameter of this other circle. Now, because we see this big point that is near the center of our circle, that's one of the 3 assumptions you can make in geometry, is if there's a big black dot near the center of a circle, you can assume it is the center of a circle. So we've got the diameter of these 2 semicircles, right? Because this line goes through the center, then we can assume it's the diameter. So we've got 2 half circles. Now, if we put 2 half circles together, obviously, what do we get? We get an entire 180-degree circle. So this left length plus the right length is, we have the circumference of a whole circle, right? So we have that length plus, we're going to add up this top 13, and then we're going to add up this bottom 13. So really, this is just the circumference of one circle plus 13 plus 13 is the perimeter of this. So we didn't need any fancy arc length for this, and that was a nice little trick. So the circumference of the circle, I'm going to use pi times diameter since we have the diameter. So we've got 6 times pi, or 6 pi, plus 13 plus 13. So that comes out to be 6 pi plus 26. That's absolutely an okay way to leave an exact answer. If you would like, you could plug that into a calculator with an approximation. It doesn't tell you need to approximate or get an exact answer, so I'm always going to choose an exact answer. Okay, so on the next one, let's look at what we got. Now, this one does at least tell us we've got 2 right angles here. And since we do know here that opposite sides are congruent, and we've got 2 right angles, I believe we could figure out that this is a rectangle. Oh, we know more than that. We actually, because this is 3, this radius is 3, this radius is 3. So yeah, opposite sides congruent. It's a parallelogram. We got at least 1 right angle. In fact, we got 2, so that means that all the angles are right angles. So yeah, this is a rectangle. Okay. No assumptions there. We could prove that. Okay, so it says find the perimeter of the shaded region. So let's break it down, right? Obviously, we've got this entire top length. Oh no, we've just got the 6 length. So we've got a 6 plus, and then a quarter of a circle, right? So we've got the 90-degree portion of the circle. And then plus, we've got another 6, and then plus another quarter of a circle. And notice these circles both have the same radius of 3 and 3. So of course, if I add up a quarter of a circle plus a quarter of a circle, really I've got a half of a circle. So what I've got is I've got 12, the 6 plus the 6, plus I've got a half of a circle that has radius 3. So let's go ahead and figure out the length of that. Okay, so I'm going to switch over here to another color. I've got 180 degrees out of 360, which we know simplifies to be 1/2 of my circle, times the entire circumference of the circle is 2 pi r, or 2 pi 3, or times 6 pi. So if the entire circumference of the circle is 6 pi, and we've got half of the circle, then this value right here for half of the circumference ends up being half of 6 pi, or 3 pi. And then plus that distance of 12. So notice how I broke it into 4 parts. 1, 2, 3, 4 to write it out. And then I joined the kind of like terms, right? I said 6 plus 6 is 12. And then I also said, well, half or a quarter of a circle plus a quarter of a circle, as long as they have the same radius, is equal to a half of a circle. So that gives us a value of, and I like writing the 3 pi first for no apparent reason, just like I'd write a 3x first. So 3 pi plus 12 as our circumference. So I'm going to cut off there. Hopefully you enjoyed the video and that's clear. The next video will be about finding a fraction of the area. So using the same idea, except instead of with perimeter and length or circumference and length, we'll be dealing with area and regions of a circle.